Okay. Alright, before I talk about cylinder head and camshaft selection, I wanted to clear up how we get to determining how much horsepower a given cylinder head or camshaft is capable of supporting. So, how much horsepower will my cylinder head support? The key thing here is cylinder heads. We're just going to talk about cylinder heads. Everything else is built around the cylinder heads, and that's just because the cylinder heads is your point of most restriction on almost every engine. So getting the airflow through the cylinder heads and around that valve and in the chamber is the biggest part of making power. Everything else is just making sure you can support that airflow. So how much horsepower will my cylinder head support? Superflow has a formula out there. If you're watching this video, there's more than likely a chance that you've seen the formula out there. And that formula is your airflow, your peak airflow in CFM multiplied by 0.257, usually rounded to 0.6, times the number of cylinders. Okay? But no one can ever tell you why this number. Okay? The reason for that number is at 338 feet per minute, this is 0.3 Mach, okay? 0.3 Mach, airflow behaves as an incompressible fluid. The reason this is important and why we can make some inferences based off that is once airflow goes beyond 338 feet per minute inside the port, it starts to become very turbulent because it starts stacking up on itself. On a supercharger, you have a very tightly packed, like I said in the last video, oxygen content inside the same cubic foot. Alright, this is a little different because you have what's called turbulent flow. You start going away from your laminar flow and start getting more turbulent, more and more turbulent. And because of that, the air turns around and hits itself and you have less flow through the cylinder head. That's why every cylinder head at some point, no matter how much more you lift the valve, you have port stall. It will not flow any more air. And this is that point when your port is going, the airflow demand is so saturated that you have turbulence. So below 338 feet per minute, which is 0.3 Mach, airflow behaves like an incompressible fluid. Yes, it's air. Yes, it's compressible, but it has much more like a behavior of an incompressible fluid. So it's easy to make inferences based off that. Since the amount of airflow an engine can move directly proportional to the power potential we can estimate, it's given net airflow. So basically, if you know what the net airflow is, okay, net being what you're actually flowing through the engine, not your gross, not just putting your cylinder head on the flow bench. We talked about this in other videos. Not just doing that, putting your intake manifold on there, putting your throttle body or your carburetor on there, put your air cleaner on there, put your headers on for your exhaust that you're going to be putting on the car. Those airflow numbers are what's gross. I'm sorry, net. Okay? Your net airflow. Your gross airflow is just your cylinder head with a little plate on there just to simulate just the cylinder head's capability. Okay? So, once we know that, the formula is a percentage of 0.3 Mach is what this Superflow number is, a percentage of 0.3 Mach. If we know port velocity and average area, we can predict power potential. Okay, and we're going to go into my cylinder heads, an example. There's a little bit of a glare right here, but I'll move the camera here in just a minute. So, how to find your horsepower potential. First thing you got to do is find your average piston speed. Okay, so for your combination, take your stroke times the RPM that you're going to run, not that you want to run, but what you're going to run, and be honest with yourself here. Divide that by 6. That'll give you your average piston speed, not your fastest point of piston speed, but this will give you your average, which is what's important for this formula. All right, find port velocity. Port velocity is piston speed, which you calculated here, divided by 60. Okay, multiply that by your bore squared. So I'm using a 350 small block, so my bore is 4 inches. 4 inches squared. Divide that by their average port cross-sectional area. Now, in cylinder heads, there is a minimum cross-sectional area That's the smallest point inside the port. It's not as important as people think it is. It does affect where you're going to have some additional turbulent flow, because your airflow going through, you can look at Bernoulli's principle. I think I talked about it in another video. You know, your air, you've got to cover the same amount of distance and the same amount of airs in and out, okay? And it has to go faster through that smaller point. So at some point you get what's called port saturation, where it just simply can't get any more air packed in there given atmospheric pressure. That's what a supercharger helps with, is getting that additional oxygen content packed into a smaller package, so that when it, even though it's going through that port, even though it's getting compressed, but you're already compressing it with a supercharger. So if you get 300 CFM and your port stalls at 300 CFM, but you have a supercharger on there that's adding artificial atmosphere or turbo, all doing the same thing, artificial atmosphere, you're going to have more oxygen content per CFM, so you're going to still make more power. But anyway, I talked about that on another video. So you take your bore squared, average port cross-sectional area is your entire port, okay? You can, there's calculators out there, but the best thing to do is, if you have your cylinder heads, is to measure, okay? Measure the cross-sectional area from the beginning of the port to the end of the port, okay? It takes some time to do this accurately, but if you want a good product here and you want to know what you're really capable of, and if your port's too small and you need to work on making it a little bit bigger, or you need to work on your transitions to get it to flow more, that's what this is for. Now, if you're trying to decide on what cylinder heads to buy, people like Airflow Research and stuff, they will put on there what their minimum cross-sectional area is. Well, if you know that that's the smallest point, you can usually take that, add 5 or 10% to that minimum cross-sectional area, and that'll be your average. And it gets pretty close. Again, it's not going to be perfect. It's not going to give you a perfect number. But you need your average, not your minimum cross-sectional area, your average port cross-sectional area. Okay. Then you're going to find the percentage of 0.3 Mach. So that's just your port velocity, which is what you're going to get in this formula, divided by 338. Okay, 338 is 0.3 of Mach. Mach 1. Okay. Find horsepower per CFM. You're going to take what you get out of your port velocity divided by 338. You're going to multiply that by 0.3. Okay. Then this is going to give you a percentage of 0.3 Mach, and this is going to tell you what that is. Say, you take your percentage, multiply it by 0.3 Mach. This is find horsepower potential. So horsepower per CFM, which is what this is going to give you, multiply by your net CFM, and the number of cylinders. When I say net CFM, so, and I'm going to talk about this more in the next video, but your camshaft has a very specific ramp rate, okay? So if you have 600 lift on one cam and 600 lift on the other cam, how they get to 600 lift is different depending on duration. Even if they have the exact same duration, exact same lift, you will still have differences in airflow, because how aggressive is that lobe, or how soft is that lobe, okay? Is it asymmetrical? Is it only going one round, aggressive intake ramp and a slow exhaust ramp, a softer exhaust ramp? That all affects airflow, and I'll talk about that in the next video, or one of the next coming videos when I talk about camshaft selection. But you can directly affect more torque or more peak horsepower based off how the lobe is designed, given the exact same duration, exact same lift, everything. And I will prove that to you. But anyway, so net CFM, and the reason why I brought that up is, when I say net CFM, I'm not saying what Superflow says, use your peak airflow number. You actually don't want to use the peak airflow number. You want to use the airflow that from the time your camshaft leaves the seat until it comes back on the seat, okay? From 0 to 100,000s, 200,000, 300,000s, 400,000s, 500,000s, 600,000s. My cam goes 600,000s after hot lash, so that's why I'm using that as an example. But you take how much time, how many duration in degrees it's at each one of those lifts. So at 1, 2, 3, and 4, and 500 thousandths lift, it's going to hit that point twice. So I'm going to use what the CFM, it flows on the flow bench at each one of those lift values. The beauty is cylinder head manufacturers will give you that. Okay, they will give you those flow figures. What you do with the flow figures is, this is where your camshaft comes in. You can use the exact same cylinder head on two identical combinations. Absolutely nothing different about them but the camshaft and the load profile. And you can affect where that power comes in. Is it going to be more torque? Is it going to be more power? And again, I will prove that to you on the next video, or one of the next videos. Then the next thing you're going to do is you're going to take your horsepower potential that you just calculated. You're going to multiply it by volumetric efficiency. If you're naturally aspirated, a lot of the time that's going to be 85%, 80 to 85%. It could be as high as 100% on a good built race engine, and it can even exceed that if you really get it correct, like your NHRA. A lot of those guys, they're making over 100% non-boosted. But if you're boosted, your volumetric efficiency typically is going to be higher than 100%. And then you're going to take away your losses. So for example, I'm using a root style supercharger. A root style supercharger uses horsepower to make horsepower. In mine specific, at 6,500 RPMs, which is what I'm going to use for my example, it uses about 100 to 110 horsepower to turn that blower. So I've got to subtract that from my potential, because it's not potential anymore. That's why a turbo on my application making the exact same amount of boost at 6,500 RPM will have about 100 more horsepower. And that's because, you know, it's not taking all that additional horsepower to turn the blower. Anyway, so then you're going to subtract your drivetrain losses if you know them. My 700 R4, it's with my, I've done on the engine dyno and then on the chassis dyno, and I lost about 100 to 110 horsepower. I got 31.5-inch tall mud tires, 4-wheel drive. So your transfer case, you got 700 R4 automatic. It eats it up. So you have those things you got to keep in mind. But if you know what your losses are, you can put that in here and it'll give you more of a wheel horsepower number. So we're going to work through an example of my cylinder heads and what I should realistically expect by them. So 3.48, 350 small block times 6,500 RPMs divided by 6, 3,770 feet per minute piston speed. You're going to take piston speed divided by 60, multiply that by the bore, which is a 4-inch bore. 4-inch bore, 3.48-inch stroke, 349 point something, with basically a 350 small block stock, because I'm going to use a ZZ4 short block for this specific build. And then you do your area, okay? So your average cross-sectional area, mine is 0.211. So then you're going to turn that average cross-sectional area into actual tubular area. Okay, so pi times that divided by 2, which is your radius, so pi times radius squared, and that'll get that number. This will give you your feet per minute. Okay, you take your feet per minute. This is how quick the air is moving through my port. Divide that by 338. That gives me a percentage of 0.3 Mach. You take your percentage of 0.3 Mach, multiply it by 0.3, and that's 0.2552. That means that my cylinder head's port velocity is a little bit slower, just a little bit, than what Superflow is saying, 2.257. Okay, is that a much? Maybe 5-ish horsepower at it. It's not much. So if I were, and the reason why mine's like this is because I increase some volume areas inside the chamber to allow for additional RPM because I ran out of port volume. Can I raise this number? Yes, but I'll also lose power potential at the peak RPMs. Okay, so there's a balancing act here. If you had a port that flows 338, it's gonna be very torquey, but depending on your port volume, unless that port is developed like, you know, a Formula One type car where it's, you got all kinds of computers and you know exactly where to do stuff to get it in the right spot. There you go. Now this is where people with over 100% volumetric efficiency typically live, is when they're above 300 feet per second in the port, and they can still support with a volume without running out of breath. Anyway, 0.2552, so 0.2552 multiplied by, this is my average flow, 232 CFM. So my cylinder heads flow 285 CFM, okay, at 600 thousandths lift. Now, the problem is, when you put in my manifold, the blower plate, the throttle body, and everything, it drops it down to about 260, 265 CFM peak. Now, that's peak flow. So that's not what I need. I need the average flow, because that lobe is going to go up and it's going to go down. Because if you were to use your peak number, that's just assuming that your your valve is completely open and completely closed. Okay, on a Koenigsegg or something like that that uses hydraulically charged valves and they can do that, then great. But on our regular push rod 2-valve motors, yeah, you're not going to do that. So you're going to have a ramp curve. Okay, so it's not going to flow the same amount of air throughout the entire ramp curve. So you need to take your average flow. Now I have a computer simulation that shows fluid dynamics, and I can put in exactly what the head flows, and I can put in the exact lobe characteristics, and it'll tell me what my flow is at every lift. Not everybody has that. So you can use just a basically rule of thumb, and you can even ask your cam manufacturer for a lobe curve, and it'll tell you, you know, it'll show you a graph of what the lobe ramp rate and everything is. They have to give that to you, and if they don't, then I would go to a different cam manufacturer. But anyway, you can do that if you want to spin down and do the math. But 232 is what my cylinder head's average flow is throughout the entire ramp curve, okay, which is pretty dang good. 232 times 8, 473, okay? Now, find estimated horsepower with VE, okay? 473.6, multiply that by 1.5. Okay, I'm supercharged, guys. This 473 is what I can expect naturally aspirated at 100% volumetric efficiency. Okay, we already know that I wouldn't be there, so it would be less than this. So if I was naturally aspirated, I'd probably multiply that by 85% roughly. Okay, and you can get that figure by here. If you look, that is a multiplier of 0.3 Mach. Okay, this is what you can typically use for your VE. Okay, it is going to give you a very close number. So 85% volumetric efficiency is what I would be if I was naturally aspirated, times 0.85. That means that my truck, naturally aspirated, would make 402 horsepower. Okay, 402 horsepower. Now, I'm not naturally aspirated, I've got a supercharger on it. Now, and I put 1.5 as a multiplier here, and I can tell you why. Okay, I am running 12 pounds of boost. Now, if you run the calculation, that would be 1.8, okay, because 12 pounds of boost divided by 14.7, which is your atmospheric pressure, that means I'm going to be adding 81% more artificial atmosphere. The problem is my supercharger is a root style supercharger and it generates a lot of heat, so it's not going to be 100% effective. Plus it has air that can be, once it's spinning really fast, you have what's called slip, and that's a technical term, slip. And it basically is where the air is churning and it'll actually catch back in the rotor and come back out, and you have reversion. So 60% is typically a very good figure. 60% of your amount of boost on a root style supercharger. Now your newer ones are going to be much more efficient, but mine's an old school 2-lobe rotor, so it moves a lot of air, but it's not as efficient. Okay, If you can see, that's 0.489%. Okay, I just rounded that up to 0.5 for easy math. Okay, but if I add a 1 to that, that's 1.4897. Okay, and that's close enough, 1.5. Okay, now you take 473, multiply by 1.5, and then I subtract that 100 horsepower that it takes to spin my supercharger. Okay, 605 horsepower. So my combination I built specifically because I wanted a 500 horsepower to the tire car. That's what I wanted. That's what I wanted my truck to be. Okay, I wanted it 500 horsepower. Well, I lose about 100 horsepower with my drivetrain losses. I already know that. And it doesn't change because you make more power. People do that multiply by 80%. Like I have 20% drivetrain loss, 15% drivetrain loss. That's a complete load of crap. Okay, it'll give you a rough idea, sure, if you can get the percentages right. But if you really want to know, you need to put the engine on an engine dyno, put it in a car, and then see what the horsepower losses are. Okay, your horsepower losses at that point are going to be more realistic of how much drivetrain is affecting your power. Now you can take that figure, and if you make your car have 2 times as much horsepower, you don't take 80% of that, because then you just like tripled how much drivetrain losses are. Are they going to increase a little bit more? Yeah, a little bit, and that's because of heat. You additional power, additional heat, you're going to have the heat losses, but it's not going to be 20% of everything that you do to it. So if you have 1,000 horsepower, you don't do 20% of that for your drivetrain losses. It's just not realistic. So what you would do is, I know that I lose about 100 to 110 horsepower with my drivetrain. Okay, it's pretty terrible, but that's okay. It's a truck, it's 4-wheel drive, it's got all kinds of stuff to go through, and I got 342 rear gears. It's a tall gear, and that's just because it makes all kinds of torque. I don't need a 410 or a 435 gear for the street. So that 410 gets me in the RPM band I want to be when I'm cruising on the freeway, but it also keeps me from blowing the tires out really bad, kinda. But anyway, so 1.5% minus 100, 605. So take 100 more off of that for my drivetrain losses. I've got a $500 truck, or 500 horsepower truck. It looks like a $500 truck, but anyway, so that's how this all works. If you got questions, put it on the comments, and I'll try to answer. I know there was a glare there, so I wanted to move this to where you could see what I'm doing here. And if you can't read any of this, let me know and I'll get with you on it on the comments. But anyway, so that's where I did all this to show why this formula is a good method. Okay, this 257 is basically 85%. Okay, and they're assuming 85% volumetric efficiency. So if you take your average flow, and the way you can do a quick and dirty of this is you take your flow figures at your 3 mid lifts. Okay, you take away your 100,000ths lift and you take away your peak lift, because if you're flowing it to 600 lift, my flow numbers at 600 lift and up are relevant, because it's going to get 600 and it's going back down. So your flow figures at 3, 4, and 500,000ths lift on my combination, you take those 3 numbers, add them all 3 together and divide by 3, you're going to get a very similar number to this 232. It's a little bit higher, but it's actually a little bit lower than on this, but because my lobe is a circle track lobe, it's very much so designed for torque. Okay, so my lobe is very aggressive, and that helps me get more time, more duration at that 2, 3, and 4,000ths lift, which is what I wanted out of my camshaft. And I'll go into why I did that later. But basically it's to favor torque, because it's a street truck, not a race truck. But anyway, That's how you do this. Alright, thanks.